Hey there. You shared a fascinating paper with us, and, well, it analyzes these powerful language models, like GPT.
Oh, interesting.
Yeah, and it uses this mathematical framework called Markov chains.
Okay.
It's called large language models as Markov chains. And it really helps us kind of understand what's going on under the hood of these things.
Yeah, it's pretty amazing how this research shows that, even though LLMs, they seem to have this magical ability to generate all this text, endlessly,
Right.
their behavior, you
Yeah.
can actually represent it mathematically.
Okay, so let's unpack that a bit.
Yeah.
What is it that makes this mathematical representation even possible?
Well, at their core, these models, they work with a finite vocabulary, right?
Oh.
And they operate within a limited context window.
Hmm.
So that means the amount of information they're processing at any given time is fixed.
Okay.
So even though they're trained on these massive data sets,
Right.
their potential outputs, they're limited in a way that allows us to kind of map them out,
That's neat.
It is.
Yeah.
The paper dives into this using what's called a transition matrix, which they denote as QF. And this matrix, it maps out all the potential transitions between different word sequences. They call these word sequences states.
Okay.
And you can actually see a visual representation of this in Figure 1 in the paper.
Okay, so we have this map
Yeah.
of all these potential pathways,
Mm.
but how does the LLM, how does it actually decide which path to take? It can't be totally
Oh, you're
random.
right. It's
The
not
paper.
random.
Yeah.
The training data plays a big role here. So the probabilities that are associated with each transition in the matrix, those are determined by, the vast amounts of text the LLM has been trained on.
Right.
And that's how the model learns to generate text that is coherent and grammatically correct,
It's learned all the
It'll
rules.
learn the rules, yeah.
So this is where it gets really interesting, to me at least. The paper talks about temperature and how it influences the LLM's output.
Yes, temperature. So temperature is a parameter. It's used to control the randomness, or you could say the creativity of the model's output.
Okay.
So a higher temperature, that makes the LLM more likely to choose less probable transitions in that matrix.
Okay.
So that can lead to unexpected, more creative results.
So it's like a dial you can adjust to make the model's output more predictable and more surprising.
Yeah, that's a good way to think about it.
Yeah.
What's interesting is the paper found that temperature affects not only what the LLM generates, but also how quickly its Markov chain reaches kind of a state of equilibrium.
Equilibrium. Can you explain that? What does that mean, like, in the context of LLMs?
Sure. Think of it as a point where the LLM kind of settles into a predictable pattern of output based on, its training and the input you give it.
Okay.
And this equilibrium is called the stationary distribution of the Markov chain.
And you said that temperature influences how quickly the LLM reaches this state.
Yes, according to the paper's findings, in the role of the temperature section and Figure 4, higher temperatures, they lead to faster convergence to that stationary distribution.
So a hotter LLM settles into these predictable patterns more quickly?
Yeah,
That's really fascinating.
it is. And to kind of illustrate these concepts further, they use a simple toy model.
Oh, yeah.
It's in section 3.2. It's based on a sequence of zeros and ones where the next digit in the sequence, it depends on the sum of the previous three.
Oh, okay.
So very, very simple.
The toy model. It's always great to have a simplified example to help visualize these complex ideas.
Yeah, and this toy model, they represent it as a transition matrix shown in Figure 3, and it demonstrates many of the same properties that we see in the more complex QF matrix.
So even in this simple model, we see this like structure of potential pathways and transitions that the LLM can take.
Exactly. And what's fascinating is that this simple model, which they visualize in Figure 4, also exhibits a unique stationary distribution, just like those more complex LLMs.
Okay, so we have these transition matrices
Mm-hmm.
representing all the possible paths the LLM can take.
Right.
But the matrix itself, it's not just like a random jumble of numbers, is it? The paper mentions something about its structure being important.
You're right. It's not random at all. So, Proposition 3.1 in the paper, it points out that the transition matrix QF, it's sparse. That means it has a lot of zeros,
Okay.
and it also has a specific block structure, which they explain further in the text after the proposition.
Okay.
And these properties, they're really crucial for the mathematical analysis of the LLM's behavior.
So these structural features of the matrix, they give us a way to actually analyze what the LLM is doing. more effectively.
Exactly.
Okay.
And this analysis, it reveals some interesting distinctions between different types of states within the Markov chain.
So you were referring to like the transient and recurrent states mentioned in Proposition 3.2.
Precisely. The paper explains that the transient states, those act like stepping stones, leading the LLM towards those recurrent states, which, ultimately form kind of a core set of possibilities.
So the LLM bounces around, explores those different paths, but ultimately ends up in this core set of recurrent states.
That's right. It kind of gravitates towards those. And this is consistent with the idea of the stationary distribution we talked about earlier, right? That equilibrium state that the LLM eventually settles into.
It's all starting to come together now. This Markov chain framework, it really provides a powerful way to visualize and analyze, what these LLMs are doing.
Absolutely. And the paper goes even further. It explores how we can use this framework to understand, the LLM's ability to generalize. So, how well it performs on data it hasn't seen before.
Yeah, that's one of the most impressive things about these things,
Yeah.
how they can go beyond simply mimicking the data they've been trained on
Mhm.
and actually generate novel and meaningful text.
Absolutely. And this generalization ability, it's closely tied to another really fascinating aspect of LLMs, in context learning.
Right, so in context learning, that's the LLM's ability to adapt to new information without being explicitly retrained.
Exactly. It's like they're constantly learning on the fly.
Yeah.
And the paper, it actually draws a connection between in-context learning and this concept of mixing time in Markov chains.
Mixing time. Okay, remind me what that refers to.
Sure. So mixing time, it's the time it takes for the Markov chain to reach its stationary distribution, that state of equilibrium.
Oh, right. That home base that we talked about earlier.
Exactly. And the paper suggests that the faster an LLM's Markov chain can reach this equilibrium, the more effectively it can learn from, new information in context.
Oh, okay, I see. So it's like the model's constantly adjusting its internal map, its probabilities,
Yeah,
as it encounters this new data. And the faster it can do that, the more adaptable it becomes.
that's a good analogy. Now, to really put this Markov chain framework to the test, the researchers didn't just rely on theory. They actually ran experiments using real-world LLMs.
That's
So
right.
it's always a crucial step.
Always good to see what happens in practice.
Always good. So they tested their ideas on Mistral, Llama 2, and Gemma. And these are described in section 5. And the goal here was to see how well these LLMs could learn Markov chains in context.
So they're basically seeing if these LLMs, which are trained on this massive amount of text data, can they actually learn the specific rules of a Markov chain just by observing, a sequence of its states?
Exactly.
Okay.
And their findings, which are detailed in the figures included in section 5, they confirm that these models, they do exhibit those predicted scaling laws when learning Markov chains.
Okay, so meaning that the relationship between like the amount of data they need to learn and their performance, it actually matches the theoretical prediction.
Exactly.
Okay, that's pretty compelling evidence.
It is. Now, one of the most surprising findings of the paper is how these LLMs actually stack up against a more kind of traditional frequentist approach to learning Markov chains.
Oh, okay, I'm intrigued. What is this frequentist approach and how does it compare to the way LLMs learn?
So the frequentist approach, it's essentially a brute force method. It's based on counting. So you simply count the occurrences of, different states in the Markov chain to try to predict future states.
Oh, okay, so like if I see the sequence 0 1 0 1 0 a bunch of times, then I would predict that a 1 is most likely to come next.
Exactly. Yeah, pretty straightforward.
Yeah.
But here's the surprising part. The paper found in corollary 4.3 and the discussion that follows that LLMs can learn Markov chains much more efficiently than this frequentist approach.
Really?
Yes.
How do they measure that efficiency?
So they look at what's called sample complexity. That's the amount of data that a model needs to learn accurately. And they discover that the amount of data that an LLM needs, it scales linearly with the size of the vocabulary. So if you double the vocabulary size, you roughly double the amount of data needed.
Yeah, that makes sense.
Which makes sense. However, the frequentist approach, it scales exponentially with the number of possible states in the Markov chain.
So as the chain gets more complex, the amount of data needed for the frequentist approach, it explodes.
Exactly.
Yeah.
And this difference in scaling, it's a major advantage for LLMs, especially when you're dealing with these complex sequences where the number of potential states is vast.
Right.
They seem to have kind of a natural aptitude for this type of learning.
It's like they've cracked the code of sequential learning in a way that these traditional methods haven't.
Yeah, it seems that way. And this finding, it really highlights, the incredible learning capacity of these LLMs.
Yeah.
Even though they're not specifically designed to learn Markov chains,
Yeah.
they can do it incredibly well.
This is already blowing my mind. The whole idea of viewing LLMs as Markov chains, it's so insightful.
It does offer a really powerful new way to analyze and understand their capabilities. And we've only just scratched the surface.
Okay.
There's so much more to uncover here.
Well, then we have a lot more to unpack.
Yeah.
Can't wait to delve deeper into this research.
So picking up where we left off, there's another really important concept that kind of helps us understand the behavior of LLMs as Markov chains.
Okay, I'm ready for more.
What is it?
It's called ergodicity.
Ergodicity.
Yeah. So proposition 3.2 in the paper, it explains that the Markov chains that represent these LLMs are ergodic.
Ergodicity. Okay, that sounds kind of technical. What does that mean, like in simpler terms?
Essentially, it means that the LLM, over a long enough period of time, will visit all of its possible states. So regardless of where it starts, its starting point,
Okay.
it will eventually, given enough time, visit every single state.
So given enough time, it'll explore like every possible combination of words and sequences that it's capable of generating. Exactly. And the paper kind of elaborates further on this concept, stating that, this property is essential because it ensures that the chain will ultimately converge to its stationary distribution.
Oh, right, that home base we were talking about earlier.
Yes, that unique stationary distribution. And this convergence, it has, major implications for how the model behaves, because it means that, the LLM's output, it becomes more predictable after a certain point.
Okay, so even if it starts off exploring all these, this wide range of possibilities, it eventually kind of settles into a more stable pattern.
Precisely. And, the paper doesn't just stop at proving the ergodicity of these LLMs as Markov chains.
Right.
In Proposition 3.3, they also derive a rate of convergence. So this tells you how quickly the LLM reaches that stationary distribution.
Oh, okay. So how fast do these models reach their home base?
Well, the paper provides an upper bound for this rate. And, it depends on a few factors, things like the size of the vocabulary, the context window, and, of course, the model's temperature.
Temperature. It keeps popping up everywhere.
Okay.
So a higher temperature, would that mean a faster convergence?
Yes, their findings indicate that higher temperatures do lead to faster convergence to the stationary distribution.
Okay.
And this lines up with, what we were discussing earlier about how temperature affects how quickly the model kind of settles into predictable patterns.
Right.
Okay, so we've got ergodicity, guaranteeing that the LLM will visit all its states.
Mm-hmm.
And then the convergence rate tells us how fast it gets to that equilibrium state.
Right.
But the paper also goes deep into kind of the mathematical underpinnings of this stationary distribution.
Okay.
They utilize several concepts from probability theory, things like irreducibility, periodicity, and recurrent classes to establish the existence and uniqueness of the stationary distribution.
Right. So that all sounds pretty complex.
It can be, yeah.
Yeah.
But remember that toy model we talked about?
Oh, yeah.
The one with the sequence of zeros and ones?
Right.
Well, they use that to illustrate these concepts in a more concrete way.
Okay, yeah. The simplified example always helps.
It does, yeah. So they demonstrate how the toy model's transition matrix also exhibits ergodicity
Okay.
and converges to a unique stationary distribution, just like mirroring the behavior of those more complex LLMs.
So even in that simple model, we see the same principles at play.
Exactly. Now, shifting gears a bit, the paper goes beyond theory and also presents some, really exciting experimental results.
Yeah, it's always good to see the theory playing out in practice.
Absolutely.
What did their experiments focus on?
So they focus specifically on in-context learning.
Okay.
And they use several recent LLMs, Mistral, Llama 2, and Gemma.
Mhm.
These are all described in Section 5 of the paper.
Okay.
And in-context learning, again, is that model's ability to adapt to new information without needing retraining.
Right. Okay.
And the researchers, they presented these LLMs with sequences that were generated by known Markov chains to kind of test this ability.
Okay, so they're basically testing how well the LLMs can pick up the underlying patterns of the chain just by observing like a sequence of its states.
That's right. And they found that the model's performance was significantly influenced by the mixing time of the Markov chain.
Okay, mixing time. That's the time it takes to reach the stationary distribution, right? That home base.
Exactly. So did they find that, like, chains with faster mixing times were easier for LLMs to learn in context?
Yeah,
Yes, that's precisely what they found. Chains with slower mixing times proved to be more challenging for the models to learn in context.
that makes sense, right?
Yeah,
The faster the chain settles into a predictable pattern, the easier it is for the model to kind of grasp the underlying rules.
absolutely. And to kind of measure the performance of the models, they used a metric called risk. And this measures how different the model's predictions are from the true probabilities of the Markov chain.
Okay, so a lower risk means better performance.
Yes.
And did they find that risk scales with the mixing time?
They did. They found that chains with slower mixing times, they lead to a higher risk, meaning the models have a harder time making accurate predictions. And this finding is discussed further in Section 5.
So if you want the LLM to learn quickly and accurately, you need to give it a Markov chain that mixes quickly, one that
Yes.
reaches its predictable pattern quickly.
That's a good takeaway from this part of the research, yeah. And the authors highlight, this connection between in-context learning and mixing time
Right,
and its implications for how we design, tasks for these LLMs.
right. So you're giving the model like a well-structured lesson plan so it can learn efficiently.
Exactly, exactly. Now, the researchers, they didn't stop there. They also wanted to compare the performance of LLMs to a more traditional frequentist approach to learning Markov chains.
Okay. Oh, so they pitted the LLMs against the tried and true statistical methods.
Exactly, round two.
Yeah, who came out on top?
Well, the results were quite interesting. So in certain situations, they found that LLMs could actually outperform the frequentist approach, even though, again, they weren't specifically designed for learning Markov chains.
That's really impressive. It speaks to the inherent learning ability of these LLMs. Where did they see this superior performance?
So this advantage was especially noticeable when the number of states in the Markov chain was large.
Okay.
And this is described in Corollary 4.3.
So when the complexity ramps up, LMs really shine.
Precisely. And they then analyzed how this performance scales with, the amount of data the model is given.
Right. Scaling laws are always interesting. What did they discover about the LLM scaling behavior?
So they observed, as discussed in Corollary 4.3, that the amount of data needed for an LLM to accurately learn a Markov chain, it scales linearly with the vocabulary size.
Okay, so if you double the vocabulary, you roughly double the data needed.
Exactly. However, they observed that the frequentist approach scales exponentially with the number of states in the Markov chain.
Right. And that exponential scaling, that can get out of hand very quickly.
Exactly. And this difference in scaling behavior, that's what gives the LLMs, a significant edge when dealing with these complex Markov chains with many states.
Right. It highlights how efficient LLMs are at this type of learning, compared to these traditional methods.
Absolutely. Yeah, their inherent ability to learn sequences it's pretty remarkable.
Yeah.
And, the researchers didn't just limit their experiments to random Markov chains.
Okay.
They also explored how LLMs perform with more structured types of chains, like random walks.
The random walks, okay. Those are like the classic examples of, a particle moving randomly from one state to another.
Exactly. And they considered two specific types of random walks. Constrained random walks where the particle can only move to neighboring states,
Okay.
and then polygonal random walks where the particle is moving, clockwise or counterclockwise around a polygon.
Okay, so they're essentially testing the LLM's ability to learn different types of movement patterns.
Yeah, that's a good way to put it. And their experiments, which are detailed in Appendix E.3.1, showed that even for these more structured Markov chains, the LLMs, they still exhibit those predicted scaling laws.
Huh. It's like they've figured out like these fundamental principles of how these models learn sequences, regardless of the specific structure of the sequence.
Yeah, they've certainly made significant progress in understanding sequential learning in LLMs. And they also kind of pushed their framework further by studying a class of Markov chains called inner cliques and outer rims, which are discussed in Appendix E.3.2.
Inner cliques and outer rims, what makes those chains special?
So these chains are, they're specifically designed to be kind of challenging to learn. They have structures that often trip up traditional learning algorithms.
Oh, okay, so they're like the ultimate test for the LLM.
Exactly. And to make the comparison, even tougher, they pitted the LLMs against the frequentist approach in this scenario.
Okay, round two of the learning algorithm battle. What were the results this time?
Well, the findings presented in Figure 15 show that while the frequentist approach, it achieved a slightly lower error rate, the LLMs, they still demonstrated that same power loss scaling behavior.
Oh, so even though they didn't win outright,
Yeah.
they still performed remarkably well against, like a specialized algorithm on this challenging task.
Yeah, absolutely. And, their consistent scaling behavior across, such a diverse range of Markov chains, it further validates, the robustness of their theoretical framework.
Yeah.
It's a strong indication that this framework can be reliably used to understand and predict, the performance of LLMs on various sequential learning tasks.
It's like they've given us a new toolkit for analyzing LLMs,
Yeah.
helping us see past the surface and understand, like, the mathematical principles behind their learning abilities.
But that's a great way to summarize it. And they also, they took into account, the important role of tokenization in their experiment.
Tokenization, so that's like breaking down language into individual units that the LLM can process.
Yeah, exactly. And different LLMs, they use different tokenization methods, which can, impact their performance, particularly when dealing with like numerical values.
Okay, so even if two LLMs are processing the same information, their different kind of dialects can lead to variations in their output.
That's a good analogy, yeah. So the researchers, they carefully considered the tokenization methods of each LLM they tested to ensure that their findings weren't skewed by these differences. And they specifically highlight this consideration in section E.4, focusing on the Llama 3 family of models, which are known for handling numerical values quite well.
Okay, so they were very thorough in making sure that their comparisons were like fair and accurate.
Yeah.
What do they find about the Llama 3 models?
So despite having this, advantage in numerical tokenization, the Llama 3 models actually performed, slightly less impressively than some of the other LLMs in the Markov chain learning
Oh,
tasks.
that's surprising. So it suggests that like there are many factors at play in LLM performance beyond just tokenization.
Exactly. It's a complex interplay of, the model's architecture, its training data, and the specific task at hand. And to explore the limits of their framework even further, the researchers actually went beyond Markov chains.
Oh, wow.
And they tested their framework on dynamical systems.
Dynamical systems. Okay. So those are systems that like evolve over time, right? Like
Yeah.
like the weather or the stock market.
Exactly.
How do they apply their framework to something like that?
So they focused on four specific types of dynamical systems described in a paper by Lewin Walls, and these included geometric Brownian motion,
Okay.
a correlated Gaussian process, an uncorrelated Gaussian process, and an uncorrelated uniform process.
Wow, that's a mouthful. So they were essentially testing if their Markov chain framework could be used to understand how LLMs learn and make predictions about systems beyond just language.
Precisely. And their initial results, which are presented in Figure 17, they're quite promising. They observed that the LLMs were able to learn and make predictions that aligned with how those dynamical systems are expected to behave.
That's a really exciting finding.
Yeah.
It suggests that this Markov chain perspective, it could be much more broadly applicable than we initially thought.
It could. It could potentially unlock new ways to, analyze and understand complex systems in many different areas.
Yeah.
And this finding opens up a whole new avenue, for future research in the field.
Like we're seeing the beginning of like a new approach to scientific discovery,
Yeah.
where LLMs could be used as like these powerful tools to model and predict, complex phenomena.
Now, to kind of wrap up our discussion of this groundbreaking research, let's bring it back to the central takeaway.
Okay, what's the core message that we should be taking away from this deep dive?
So the core message is this: viewing LLMs as Markov chains, it provides us with a really powerful and insightful framework for analyzing and understanding, what makes them tick.
Yeah.
It sheds light on those factors that influence their behavior,
Mhm.
from the structure of their internal representations to their ability to learn, generalize, and adapt.
It's been an amazing journey through the world of Markov chains and LLMs. We've covered a lot of ground, the theoretical foundations, the experimental validations, and even, hints at potential applications beyond language modeling.
It truly is remarkable work, and we've really only just begun to explore the possibilities.
I can't wait to see where this line of research leads in the future. But before we get too far ahead of ourselves, let's acknowledge the researchers who brought us this paper.
Mm-hmm.
Their insights and rigorous analysis have expanded our understanding of LLMs in a really profound way.
Absolutely. Their work has laid the groundwork for a new era of research that will be, both intellectually stimulating and practically impactful.
On that note of appreciation, we'll wrap up this part of our deep dive.
We've explored some remarkable findings in this research, but there are a few more interesting points that I think you'll find fascinating.
Okay, I'm all ears. What else? What else caught your attention?
Well, the way they connected these theoretical concepts to the real-world challenges of training and evaluating LLMs, it's particularly intriguing. For instance, in Section 4, they delve into the problem of data sparsity,
Right.
which becomes especially relevant, during that pre-training phase.
Data sparsity. So
Yeah.
that's the idea that even with these massive data sets, LLMs are really only exposed to a tiny fraction of all the possible input-output combinations, right?
Yes, exactly. They highlight the scale of this issue by looking at GPT-3,
Okay.
which is a model trained on a data set of 5 by 10, 11 tokens.
Hello?
That number seems massive, but it's actually dwarfed by the number of potential combinations represented in its transition matrix QF,
Right.
which they estimate to be 109,632.
Wow, that's almost impossible to even comprehend.
It is.
It really underscores the challenges of training these LLMs to generalize well.
It does. And this sparsity issue really highlights just how efficient LLMs are. Despite seeing such a small fraction of, the possible input-output space,
Right.
they managed to learn remarkably well.
It's like they're able to grasp like the essence of language from a limited set of examples. Inferring the underlying rules and patterns.
Exactly. But the paper goes beyond simply identifying the problem.
Sure.
It also offers some insight into how LLMs might overcome this data sparsity challenge by connecting it to the concept of recurrent and transient states
Okay.
within the transition matrix QS.
Right. We touched on these states earlier, but could you remind me of their significance?
Of course. So if you recall the transition matrix QF, it captures all the possible transitions an LLM can make between different states or sequences of words.
Right.
Transient states are those that the LLM might visit initially, but it's unlikely to return to. They act as stepping stones.
Leading to the more stable recurrent states.
Yes. Recurrent states represent kind of a core set of possibilities where the Markov chain, and by extension the LLM, is most likely to settle.
So the LLM kind of explores various possibilities initially, but ultimately gravitates towards these core recurrent states that represent like the most likely patterns in language.
Precisely. And the paper proposes that this structure of transient and recurrent states,
Yeah.
it could be one way that LLMs deal with data sparsity.
So instead of trying to learn every single possible combination, they focus on the ones most likely to occur in real-world language. It's
Yeah.
kind of like prioritizing the most important clues in a complex case.
That's a good analogy.
Yeah.
And this insight into the structure of the transition matrix
Yeah.
and the role of these different states,
Right.
it helps us understand how LLMs learn so effectively from limited data.
It provides a glimpse into, the strategies these models are using to make sense of this vastness of language.
Indeed. And they provide experimental evidence to support this theoretical insight, demonstrating that real-world LLMs, they exhibit this behavior, converging to recurrent states and learning effectively, even with limited data.
Okay, so it's always good to see the theory backed up by real-world observations.
Absolutely.
Now, you mentioned another fascinating aspect of the paper. What was that?
Their discussion of in-context learning and its connection to generalization was particularly interesting.
Right. In context learning is, what makes LLMs so adaptable.
Yes.
They can pick up new information without needing retraining.
Right.
How does the paper link this to generalization?
So they connect it to the concept of mixing time.
Right.
Remember, that's how quickly a Markov chain reaches its stationary distribution.
Right.
They suggest that the faster an LLM's Markov chain reaches equilibrium,
Yeah.
the better it will be at in-context learning.
So the quicker it finds that home base,
Yeah,
the more readily it can integrate new information and adjust its behavior.
precisely. And they provide a theoretical framework to support this connection.
Yeah.
They even derive bounds relating the model's, in-context learning ability to the mixing time of its corresponding Markov chain.
So they're not just observing this phenomenon, but they're providing like a mathematical explanation for it, which could then be used to design and train even more adaptable LLMs.
Exactly. They take the analysis a step further by comparing the in-context learning ability of of LLMs trained on general text data
Okay.
to a hypothetical LLM that's trained specifically on Markov chains.
Okay, so the generalist LLM versus like the Markov chain specialist.
Yes, exactly.
How do they compare?
So Theorem 4.4, it states that while the generalist might not be as good as the specialist,
Mhm.
it can still achieve a reasonable level of performance, particularly with more training data.
That's encouraging.
Yeah.
It means that, even without this specialized training, LLMs can still adapt and learn new types of patterns
Oh,
effectively.
absolutely. And their analysis quantifies the performance gap between these two types of LLMs
Mhm.
using that K metric we discussed earlier, the distance metric for Markov chains.
Right. It's like having a tool to measure the difference in knowledge between the generalist and the specialist LLM.
That's a good way to think about it. And this ability to measure the performance gap, it gives us valuable insights into how effectively LLMs can transfer their knowledge from one domain, like general language, to another, like the specific rules of a Markov chain.
It really highlights their flexibility and ability to go beyond, just rote memorization and learn to generalize knowledge, which is, quite similar to human cognition.
Indeed. Now, for the final and perhaps most thought-provoking aspect of the paper,
I'm intrigued. What is it?
well, it's the question of whether this Markov chain perspective on LLMs could be applied to other complex systems
Okay.
beyond language. Things like, biological processes or social networks or even how the human brain works.
That's a remarkable thought. We've
Yeah.
been focusing on language and text generation,
Yeah.
but these LLMs, they might be capable of so much more.
They might. While the paper doesn't directly explore these broader applications,
Right.
it does suggest the possibility. The many complex systems they point out, they display sequential patterns that could be modeled using Markov chains.
So the language of LLMs, if you will, could be much more universal than we initially thought,
It could.
capable of describing and analyzing, the dynamics of this vast array of phenomena.
That's a compelling idea, and if true, it could revolutionize fields from medicine and economics to social sciences.
Yeah, it's like we're on the brink of a new era of scientific discovery
Yeah.
with LLMs potentially becoming, these powerful tools for understanding the universe around us.
It's certainly an exciting prospect, and though it's early days, this research really paves the way for exploring these possibilities.
Well, this deep dive has been an incredible journey, and I'm sure you've given our listeners a lot to ponder about the complexities and potential of LLMs.
Hmm.
Thank you so much for guiding us through this fascinating research.
It's been my pleasure. I'm always eager to explore the frontiers of knowledge, and this research certainly provides a lot to think about.
It has indeed. And on that note, we'll wrap up the deep dive. We encourage all our listeners to explore this research further, delve into these ideas, and perhaps even contribute their own perspectives.
Mhm.
The world of artificial intelligence is constantly evolving, and who knows what groundbreaking discoveries lie ahead.
That's the beauty of scientific exploration. With tools like LLMs at our disposal, the future of discovery is bright.
That's a perfect note to end on. Until next time, keep those minds curious and stay tuned for more deep dives into the fascinating world of research.